plus I cotan theta partial phi. Now minus f is partial theta f minus I cotan theta partial phi. Oh, and those would be h bar. It's tempting to cancel these two out, but remember that e to the minus I phi is being acted on by this operator. They don't commute that simply. So we get minus h bar, and the rest of this is compiled essentially compared to whatever the hell this is. You get minus h bar multiplied by minus I h bar partial phi of f plus minus I h bar squared partial phi of f is equal to h bar f. So now things are about to get really bad, which now it is time to distribute the derivatives because there's not much else we can do. Oh, there is one thing we can do. There's an h bar here and an h bar there, then double h bar here, h bar squared there, and an h bar squared there. Which means we can actually randomly cancel out a whole lot. This is plus I minus I squared is minus 1. Now it is time to keep working. I'm sorry. So you get e to the I phi. And what happens when we distribute this? Well, the first thing we're going to do is factor f into theta of theta e to the I and phi. So what you get here is e to the I phi multiplied by partial theta plus I cotan theta partial phi e to the minus I phi. Partial theta f is going to be theta prime e to the I and phi minus I cotan theta. Partial phi f is going to be im, which is going to give us plus m cotan theta. Theta to the e im theta phi. Now we can distribute this guy in here, which gives us minus 1 and minus 1 here, and minus 1 there. Then you have plus I partial phi of f is I, well, it's going to give us minus m multiplied by theta e to the im phi, and then minus partial phi squared is going to give us, well, this is going to come down twice, so minus m squared multiplied by, and this is actually going to become a plus because of the I squared, theta e to the im phi is equal to m theta e im phi. Now, we can't exactly cancel out the I and phi yet. It's going to take a little bit more time. Oh god. Well, this is going to give us e to the I phi multiplied by, when you distribute this, you get, I'm going to bring up the other blackboard. Yeah, I can bring it up as long as I make it very high. So this becomes e to the I5 multiplied by, when distributing this, you get theta double prime e to the I n minus 1 phi plus, here we are going to have to use the product rule, and theta prime cotangent theta e to the I n minus 1 phi, and then minus m cosecant squared theta, theta cotangent theta, not cotangent, e to the I n minus 1 phi. And then we have to distribute the partial phi derivative, so we get plus I multiplied by theta prime cotangent theta e to the, well, this comes down and becomes n minus 1 e to the I n minus 1 phi, and then plus I m cotangent squared theta I m cotangent squared theta, partial phi e to the I m minus 1, which makes this minus m times m minus 1. Cotangent squared theta e to the I m minus 1 phi. Minus m theta e to the I m phi plus m squared theta e to the I m phi is equal to m theta e to the I m phi. Now, we can actually distribute the e to the I theta all the way over here into this product, which makes this I m phi, this also I m phi, this is also I m phi, this is also I m phi, this is also I m phi, this is, we already changed that. Okay. Now, we can actually cancel out the e to the I m phi's. We can finally get the gratification that we've been waiting minutes to get. I love instant gratification. Theta minus m cosecant squared theta theta plus I theta prime cotangent theta minus m times m minus 1 cotangent squared theta minus m theta plus m squared theta is equal to m theta. And now, I want to comment on the remarkable fact that this thing, well, when you multiply it by sine squared theta, is exactly the equation solved by the spherical harmonic. This guy, for when we were solving the radial Schrodinger equation. Not just that, the spherical harmonic's phi component is e to the I m phi. That's it. The solution all this time was this thing. Y ln theta phi. That is the eigenfunction that solves the angular momentum equation. That's it for today, finding the eigenvalues and eigenvectors in momentum. Tomorrow, we're going to be talking about spin. similar to angular momentum, and I'll see you then.